All right, let's jump right in. Today, we're going to build a toolkit, not with hammers and wrenches, but with the fundamental ideas that every chemist uses every single day. We're talking about a toolkit for answering some pretty huge questions, like how much of this stuff is actually in here? How on earth do I separate what I want from all this other junk? And maybe most importantly, how do I know for sure that what I have is pure? So, let's get to it and assemble the chemist's essential toolkit.
But first, let me ask you something. Think about it for a second. How can a swimming race possibly be won by just 1/100th of a second? How can anyone be that sure? It's not just about having a super fast camera. The answer is something way more fundamental. It all comes down to precision.
You see, that desperate need for precision is what totally changed sports. After a huge controversy in a swimming final way back in the 1960 Olympics, officials brought in the electronic touchpads you see here. They measure time with incredible, undeniable accuracy. There's just no room for doubt. And, this need for rock-solid, reliable answers goes way beyond the swimming pool. Think about the COVID-19 pandemic. We all needed tests that could do basically the same thing. Find something incredibly tiny, measure it accurately, and do it fast. To get those kinds of answers, you need a very special set of tools. Okay, so here's our game plan for building our toolkit. First, we'll nail down the basics of measurement. Then, we'll get into how to sort out all kinds of messy mixtures. After that, we're going to look at a really powerful technique called chromatography. And we'll wrap it all up with the final quality check, how to tell if something is truly pure. First things first, the measurement toolkit. Because look, before you can do anything else in chemistry, you have to get your measurements right. This is the absolute foundation of all good science. Get this wrong and everything else falls apart. Now, to make sure science is a truly global effort, scientists all over the world have agreed to speak the same language when it comes to measurements. It's called the SI units. As you can see, that means we're measuring time in seconds, length in meters, mass in kilograms, and temperature in Kelvin. And this isn't just about being neat. This is what makes it possible for an experiment done in one lab in, say, Singapore, to be perfectly understood and repeated in another lab in Siberia. We're all on the same page. But getting things right often comes down to the tiniest details. When you're measuring liquids, the most important little detail is this curve you see at the surface. It's called the meniscus. Now here's the pro tip. To get an accurate reading, you have to get your eye level with the bottom of that curve. Seriously. Get down and look at it straight on. If you look down from above, it'll look like you have a less than you do. If you look up from below, it'll look like you have more. That little mistake is called parallax error, and it's a classic way to mess up an experiment. See? Precision is all about the little things. And that brings us to a super important point. You've got to choose the right tool for the job. It's like you wouldn't use a giant sledgehammer to hang a tiny picture frame, right? Same idea here. If you just need a rough idea of volume, a simple measuring cylinder is totally fine. But if your experiment needs to be super precise, you need to break out the specialized gear, like a pipette or a burette. These tools can measure volumes so accurately that they're essential when even a single drop could make or break your entire result. Okay, so we can measure things accurately. That's a great start. But what happens when the one thing you actually want is all mixed up with a bunch of other stuff? Real life is messy. So now we need tools for sorting out that mess. So how do you unmix things? Well, the method you pick depends completely on what kind of mixture you have. If you've got a solid that doesn't dissolve, we call that insoluble, think sand and water, you can just filter it. It works just like making coffee. The filter paper grabs the solid bits, and the liquid just flows right through. But what if the solid does dissolve, like salt and water? Well, filtering won't work. You need a different plan. That's where evaporation comes in. You gently heat the solution, the water turns to steam and disappears, leaving your pure salt behind. But, sometimes just boiling a solution until it's dry is a bit aggressive. If you want to get really pure, beautiful, well-formed crystals, you use a much more elegant method, crystallization. I want you to think of it like a game of musical chairs, but for molecules. You gently heat the solution to make it super concentrated, and then, this is the key, you let it cool down slowly. This gives the right molecules time to find each other and neatly arrange themselves into a perfect crystal structure, leaving all the impurities behind. So what about liquids that just refuse to mix? You've seen this with oil and vinegar in salad dressing, right? We call those liquids immiscible. The tool for this job is genius in its simplicity. It's a separating funnel. Because oil is less dense than water, it just floats right on top, creating these two obvious separate layers. And all you have to do is open the little tap at the bottom and let the denser bottom layer drain out. It's a surprisingly easy and elegant fix for a common problem.
All right, get ready, because this next tool is a real game changer. It's one of the most powerful separation techniques in our entire toolkit, and it's used absolutely everywhere, from labs that check our food for safety to forensic teams solving crimes. Welcome to the power of chromatography, or as I like to call it, a race for molecules.
So the idea behind chromatography is actually pretty simple, but it is so powerful. Let's imagine you put a single dot of a mixture, like this purple ink here, on a piece of paper. Then you let a solvent, that's the mobile phase, creep up the paper from the bottom. As that solvent moves, it starts to drag the ink along with it. But, and here's the magic, the different parts of the ink don't travel at the same speed. The dyes that are more soluble and don't stick to the paper as much will race ahead. The others lag behind. And by the end of this molecular race, you're left with the original blue and red dyes perfectly separated. So how can we use this race to identify stuff? Well, we can actually measure the results using something called the RF value. Don't let the name scare you. It's just a simple ratio. You take the distance the colored spot traveled, and you divide it by the distance the solvent traveled. Now, here's the cool part. As long as you keep the conditions exactly the same paper, same solvent, same temperature, a specific substance will always have the exact same RF value. It's like a reliable chemical fingerprint. And trust me, this is not just some neat trick for separating ink in a classroom. This is a workhorse of modern science. We're talking about chromatography being used to spot illegal pesticides in our food, to detect tiny amounts of banned drugs in athletes' urine samples, and even to help forensic scientists analyze DNA evidence from a crime scene. It's that important. Okay, so we've learned how to measure things, we've learned how to separate them. Now for the final and maybe most important part of our toolkit, the ultimate quality check. How do we know for sure if the substance we've worked so hard to isolate is actually 100% pure? And believe me, this question of purity, it's a huge deal. It can literally be a matter of life and death. In medicine, even a tiny trace impurity could cause dangerous side effects. And in technology, the silicon that's used to make computer chips has to be mind-bogglingly pure. Just a few stray atoms in the wrong place can make an entire processor completely useless. So yeah, purity matters. A lot. So how do we actually test for it? What's the secret? Well, the answer lies in melting and boiling points. You see, a pure substance has a signature move. It melts and boils at a very specific, sharp, fixed temperature. Pure water boils at exactly 100 degrees Celsius, period. A mixture, on the other hand, is, well, it's messy. It melts and boils over a whole range of temperatures. And just like that, we have a clear, simple test to tell them apart.
And this basic principle is something you see in action all the time, maybe without even realizing it. Here's the rule. Adding impurities to a pure substance always lowers its freezing point and raises its boiling point. Think about winter. When you see trucks spreading salt on icy roads, the salt is an impurity. It mixes with the ice, lowers its freezing point, and forces it to melt, even when the air outside is still below zero. That's not magic, that's chemistry. And there you have it. That's our whole toolkit, all brought together. We started with the bedrock, the absolute foundation, accurate measurement. From there, we built up our skills, learning how to separate messy mixtures from simple filtering all the way to that powerful molecular race of chromatography. And we finished it off with the ultimate quality check, using melting and boiling points to prove something is truly pure. You know, this stuff isn't just theory for a test. This is the toolkit that scientists use every single day to keep our food safe, to make sure our water is clean, and to keep our sports fair. You now get the fundamental principles behind how experimental chemistry actually works. So the only real question left is, what new challenges are you going to solve with it? Thanks for joining me on The Explainer.